here, so then you have two screens, and you can save all of it by hitting save and send it to all the students if you need to send them notes.
That's great.
Yeah, that's one of them. That's what Professor
We
Coach
could do
does.
that. We could do that. It doesn't matter.
The only problem with Professor Coach is that he doesn't write good bullet
I don't
notes.
care. Whatever it makes you happy.
Do you guys want?
Taking a video
Okay.
doesn't matter.
We're taking a video.
Oh, is it
Either way,
recording?
yeah.
Just to clip it anyway.
Yeah.
Okay, I'm gonna pause.
Then the
So we're not using smartboard?
No.
next time.
Next.
Whatever you guys want. Whatever. That's okay anyway. Actually, it's not comfortable. I'll do it. Okay. Okay, so just rehashing a little bit what we did last time, although I'm not going to go over it all over again, but just like reminding ourselves of the unit. So we did dimension analysis last time, and let's recall a few things that I want you to remember is like the fact that the speed of light is set to 1 led to the fact that the dimension of distance are equivalent in relativistic to the dimension of time. I could do it. Right?
Just dimensionless one or velocity equal to 1 meter per second?
No, we set c equal 1, which
It's dimensionless?
it's dimensionless at this point. Well, yeah, and that's why to be dimensionless, this has to be the dimension of the spatial dimension has to be equal to the time dimension. That's right. The other one that I set was h bar equal 1, and to h bar to have to be dimensionless, it means that energy is inverse distance or inverse time. So unit of inverse of unit distance, time. Let me be consistent, like t here. And since this is the same, so inverse of dimension of space. From there, we have gone to the conclusion, and I showed you that the mass of the proton has to be about 1 GeV, or 10 to the 9 electrovolt, or if you want a little bit more accurate, then it's equal to 0.938 GeV. Now, let me actually go back to a few things. Okay, so this one was convenient. To use GeV is convenient. We go to the mass of the proton, which was 1 GeV. Then what else did I want you to remember. So we know that the speed of light is 3 times 10 to the 10 centimeter per second per inverse second, or it's equal to 1 foot per nanosecond, or 30 centimeter per nanosecond, or, and you will see 300 millimeter per nanosecond, and you will see why I care. So there are several unstable particles like the and they have a lifetime usually of about 1 picosecond in their rest frame. So C tau will be if let's say the B meson or the D meson have lifetime that is about 1 picosecond, that means that C tau will be about 0.3 millimeter. So you know how much it's traveling in its own rest frame. So it's very approximate the flight distance before decay, assuming B and D are B mesons. mesons. I didn't talk too much about it beside when I mentioned the history at the beginning when I started with particle physics. So B is, there's B meson, D meson, there's all sorts of mesons, like this one has a B in it and a D bar, for example, that's one of them. B sub S will have B and S quark. D will have C and D in there.
An anti-tau.
Right, n-type. So, yes, yes. So this is kind of example of like mesons. The point is that mesons are quark antiquarks.
Quark antiquark pairs.
Pairs, right. So, yeah, thank you. So we have, this is a very approximate flight distance, 0.3 millimeter. I will get back to it in a second. Now,
Why are they quantum density C?
because they are so light, they're basically, when they decay, just like at the speed of light.
Massive particle go at speed C?
It depends what you do with it. No. No. I mean, at some point when you give it too much energy, its mass, relativistic mass is increasing. So we're talking, we have to be accurate now. We're talking about the rest mass or the relativistic mass. So we'll get into it. Let's not. So atomic distances that physicists would use will be 1 angstroms. So if we're talking about atomic, this is again just setting the ground a little bit before we do something. So 1 angstrom is 10 to the minus 10 meter or 10 to the minus 8 centimeter. Nuclear physicists or particle physicists will use the size of the proton, not the size of the atom, which is 1 angstrom. So particle physicists will use 1 Fermi, for example, as a relevant scale. And 1 Fermi is 10 to the minus 15 meter or 10, and that's approximately the radius of the proton.
Going back to the lifetime for 1 second, how do we determine something like that? I mean, that's probably just experimental. But
that's right.
My question.
Or calculate.
Why?
You can calculate it.
Why does it have a lifetime at all? Are these quark antiquark pairs not stable?
No, they're not. They're not. Like for example, the pion, and I will get to it, will decay to a muon and an anti-muon. So they will decay. There's a way to calculate it theoretically and test it experimentally. So it's not only
able to exist for a certain amount of time before it does decay.
Yeah.
What's happening during that time that's making it, that's keeping it alive until it finally decays?
What happens? What do you mean by what happens? It's just like.
I'm not even sure how to.
Yeah, I'm not so sure what. It's just like.
Why is it still able to exist for 1 picosecond?
Every particle has a probability to go if. I mean, there's not so many stable particles, right? What are the stable particles? Electron, proton. No, neutron decays to proton. So everything decays to this stable particle. So pion will also decay.
A second is more like a mean lifetime.
It's a mean lifetime. That's right. That's right. Right. It's the mean lifetime.
That makes much more sense. Okay.
Yes. It's not like by. No. This is like quantum mechanics. Everything is probability that it will decay within this time.
So some of them might decay immediately.
Yes. Yes.
Some of them might decay after.
That's right. That's right. You have basically a probability for decay.
Right.
We'll get there too. Okay. So this. So we also said that energy is unit of inverse distance. So what did we have? We have h bar c. Since h bar and c are equal to are dimensionless, then h bar c is also dimensionless. And for particle physicists, it will be 0.197 if you do the conversion, GeV per Fermi, and we did that last time, basically. So I showed that Hc divided by GeV was about 0.2 Fermi. So that was also an important fact. So I have that energy is inverse distance and time. Another, just to finish with what we did last time, another thing was cross-section. Cross-section is probability of interaction. It's proportional to an area. So cross-section, everything is interactions and probability for things to happen. That's proportional to an area usually. Usually it's proportional to an area. Now, so we call it, the units that we call dimensions are, it's called bound. I don't know why the name bound, but it's bound. Yeah, I think I don't remember what.
Yeah, because they were keeping it secret during World War II.
Oh yeah, something like that, yeah. So one bound is 10 to the minus 24 centimeters square. And what did I want?
Yeah, just redo it.
No, didn't we talk about that bar?
Yes. That's why.
No, but this specific detail.
Yes. Because she said, oh, we have to put some weird random thing.
So if we take 1 equal to h bar c, but we do square, we get that this is equal to, we're going to just play with it, this is equal to about 3.89 times 10 to the 8 GeV times picobound, 10 to the minus 12 bound.
Aren't bars already extremely small?
Yeah. Well, cross sections are very small. Remember, these particles are extremely tiny.
But picobars is even smaller.
Right. That's right. So I have.
Particles are small.
Right, they're really small.
But isn't there a point where we can't even measure that kind of distance?
I don't know.
Wait, we're talking statistics, bro.
Is the cross section for this measured?
For?
This is the cross section?
This is a cross section is something, yeah, it's measurable. Cross section is proportional if you want to do like, I don't know how you do proportional. It's proportional to an area. One bound is unit of, area, so centimeter square, for example, that's definition of bound. I just took h bar c squared, it's dimensionless, it's equal to this, and that's relevant because you can say that you can also write it as approximately 0.4 GeV, squared, GeV squared times millibound. So you have energy inverse area, one inverse energy squared proportional to area like you expect. And why is it relevant is because I told you if you want to do the cross sections of proton-proton collision and stuff like that in LHC, so you do pi r squared, where r is the radius of the proton. And we got from that if we take sigma, which is a symbol for the cross section, and we say it's proportional to pi, the size of the proton square, which is the area, it's coming out to be approximately 1 over GeV squared. And this is proportional to millibound based on this. So you already know cross sections of the LHC. So that was kind of one of the few things we talked about last time.
Yep.
Oh, so that summarized last time and what I want you to remember from last time. Now,
are we going to be doing more of this today, or are we looking at something else today?
You're gonna see.
Have patience.
So, right.
Why is that proportional to 1 millibound?
Where?
Your electron
It's just like, it's squared, everything is squared. Why didn't I write squared? It's squared, I'm sorry. Yes, it's squared, thank you. So, okay, so I said that today we did the history, we did dimensional analysis, where I introduced you to the units that are relevant to high energy and particle physics. And now what I want to introduce you, which a little bit you know about, is relativistic special relativity, which you know a little bit, and I will show you why. So I think what you have learned until now is that the laws of physics apply in any reference frame, provided that we make appropriate transformation of coordinates, and the speed of light is constant in all reference frame. This we get from Michelson-Morley. And I won't go through this, you already probably know all about it. You know about the Galilean transformation, you know why it doesn't work, you know that if we did assume that it works, then we will have to go to a frame and we will see that if the particle in that frame went at the speed of light, that means like from another frame it can look, it will look like faster than the speed of light. That doesn't make sense. So yes, Galilei broke at some point. And I won't derive, again, I thought maybe, but there is really no point. It's not what I want to show you anyway. So in every textbook to anything, you can look how you derive this Lorentz transformation. Yes, I mean, it's a few lines, but there's no point. So you have the Lorentz transformation, and what you get from the Lorentz transformation is really time dilation, that is everybody's familiar with, and Lorentz contraction of distance. So if you look at the proper distance of a stick in some reference frame that goes at the speed v, as it goes closer to the speed of light, we see shrink, right? And that's why a proton in LHC looks like a pancake, because it travels in the z direction, let's say, then it shrinks, and then in the transverse direction it looks the same. So instead of looking spherical, it will look like a pancake.
Oh, so that's a bit easier to calculate, wouldn't it be? Because we're looking at two-dimensional objects. No,
it doesn't matter. When you calculate, you calculate.
Is proton actually spherical in the stress?
Yeah. You will look because quark and gluons are all like, there's no preferred direction, but when you boost them in one direction, then it looks like there's contraction in one. The other one is time dilation, which you're also familiar with. And so I just write the two things, just two lines. Where? Here is it. What? Where's the eraser?